Okay, so today we have we have already discussed about this Tolman-Oppenheimer-Volkov equation in G is equal to C is equal to 1 units. Okay, so this is the equation. Very nice. So what are the very interesting features over here? This term, addition. Again, so pressure in the Newtonian form or non-relativistic form, this was alone. Here we have got an addition of density. Next, mass added by this another term. So pressure is again added up. So as a result, this is being stiffened up. Okay, I have already discussed these facts. Again, another interesting point. There was only r square, but now the denominator is lower. So as a result, the entire stuff becomes more and more negative. And the overall moral of the story is now, previously the gas pressure was acting against gravity, but now in the relativistic scenario, gas pressure in fact after some time it assists gravity instead of going opposite to it. Okay, so now what we are going to do, we are going to solve this equation for the most basic scenario. Okay, and what is that scenario? That scenario is constant density model. Okay, now there are various types of density models. Okay, the most interesting is this one. Rho is equal to rho 0. That means constant. This is the one we are going to talk over here. The next is give some sort of R dependence. Okay, and this is known as linear density model. R by A. Okay, this is linear density model. If you look at my lectures, you will find that we have already solved this stuff, but not for the relativistic case, but we have solved this for non-relativistic case. Next is quadratic density model. What is that? It is like this: 1 minus r square by a square. This is quadratic density model. So this is constant density model. Next is linear density model. Next is quadratic density model, you can say. Okay, now out of all this, for this particular relativistic scenario, we are going to solve the most simplest one, and that is the linear density model. Okay, okay, so fine. Okay. So you see the most general equation for the mass of a spherically symmetric object is this equation. Now if we solve this, we get this very basic result. Mr equal to 4 by 3 pi r cube. Is there anything wrong with it?
Rho into rho.
Okay. Now try to put this over here and see if you get this result or not. Check this. Okay, so remember density is equal to mass by volume. Okay, and this mass is equal to then density into volume. So we are basically missing this rho r over here. Yes. So what I am asking you is put this value of m in these two places, over here and here, and then you will find that as a result of this, you will get this reduced form. Okay. So slowly we are incorporating the expression for mr over here, and now we are going to play with this expression next. Okay, so this is the static equation. Fine. Now let's integrate this equation over here. So this is our constant density relativistic star, you can say. So now I am integrating from P, right? So dP and dr. This side is R, this side is P. So I will be integrating from r equal to 0 to r equal to r, or pressure at the center P at r equal to 0, which is Pc, to P at r is equal to r, which is just P. Okay, and now this is the form, and on this side I will be getting this part. Okay, so now I am going to solve this in two separate ways. So let's see this part. Here, let me do this substitution. This part you see, so I am substituting this as u prime. Now, if I do that, you can check for yourself that this entire integral can be converted into this very simple form, and you get this result. So, this is the LHS result. This is the result. What about the this is the right hand side part. So this is the RHS result. And what about the left hand side part? Here, let me write the denominator, this term as this, and then I can, you see, I can get this result. Again, PC to P, and this is the final result. Okay. So what I am going to do next? I am going to equate these two terms. Fine, and then we will see what happens. Have you checked all these calculations for yourself? This is very simple till now. Okay, so let's continue our play. So previously in the last blackboard work, you remember we figured out these two expressions. So now let me use this expression over here and this expression over here along with this old expression that we derived some time back. Now if I input these three things, then you can check for yourself that this is the result which we get. This is a very unique form, rho plus 3pc. Here rho plus 3p, rho plus 3pc, rho plus p, rho plus pc, and then there is this mass term over here. So here we have got density, pressure, mass, radius, all this term. Now next what I am going to do is the following. You remember we have been integrating from r is equal to 0 while pressure was Pc to r equal to r but the pressure was in general P. Now what about the surface? The surface at the radius of r, capital R. Of course the pressure will be 0 at the surface, that's why it's a surface. So if we do this integration, that means from the center to the surface, then this is the result we get. Remember, this is r equal to 0 and this is r equal to capital R. So this is the result from here that we will be getting, this simple result. Next, what I am going to do, I am going to look into the structure of this expression here. Now what I want, what is the aim of this entire calculation? What do we want to do? We have got a relativistic hydrostatic equation. What is that? dP dr, and we have got a constant density. These two things we have. What do we want generally? Pressure, how it changes. So we want the expression for pressure, that's it, nothing more. And so from this expression we want to find pressure. And for that, I have to do componenter and dividender, and then only we will get this expression. So, componenter and dividender, you must remember A by B. If there is a ratio, then A by B plus 1, A by B minus 1. Then do the division, we get this form. And from here, you will get the expression for pressure. Okay. Now this has got a very unique structure. If you look carefully, the structure is like this. The structure is like this. P is equal to sum A minus sum B whole divided by 3B minus A. This is an overall structure. Okay, see, in the examination you don't have to write all this expression, you just write what is A, what is B, and then also this is good. In fact, this is even better for understanding, right? So this is the overall structure. Now whenever in physics we have got structures like this, you have to understand there are certain things going on. Number one, in the numerator there is a competition between these two terms. Similarly, in the denominator, the competition is there, but it is reversed. Whereas the weight of B is much more. Okay, so try to understand that lot of dynamics is going on. Okay. So this is the overall structure. Yes, one thing I forgot to mention. See over here, what do we have? We have got capital R, right? No small r dependence, capital R and then PC. So basically this gives you the dependence between PC and R. That's it. Now you have to put this expression into the middle term over there. And then we will be getting rid of the PC. And then we will get this expression. So there is a journey like this. I forgot to tell you. And then you will get this. See, there is no PC in this expression. You have to eliminate PC, and that is for that relation. For that reason, we have defined this. Okay. Now this is the most important relation, and for examination also, this is very easy to memorize.
So
Just remember this form. Yes.
capital R square term.
Capital R square term. We did the derivation, integration. From there we get this term. From the middle term, we did the integration from this to this, overall integration, and so we obtained this result. Now I am going to use this result to eliminate PC in this result and get this form. Check this at home, okay? Check this at home, this is very important. But remember, the overall structure is very simple. Acha. Okay, so you see, this is the equation, pressure related to density. So you see, this is the basic form, P by rho equal to A minus B, 3B minus C. Just try to remember this. This is the one. Now what we are going to do is, we will find an upper mass limit from this very basic relation. So let's start. How to proceed? To start with, let us put R equal to 0. Very basic thing. It will just reduce all the stuff over here in a very simplified form. Let's see. Putting R equal to 0, right? So let me put R equal to 0, number 1. And number 2, let me assume X is equal to rho by rho C. Now if I do that, then you will see that this relation, this gets reduced to this form. 2m by r equal to 1 minus some form over here. And this is the x. X is equal to rho by rho C. Now see what we want. We want to find the maximum value of mass. Right? That means we want this part to be maximum. We want this part to be maximum. Now this part is equal to 1 minus something. So this part will be maximum only when this part will be minimum. Right? So let me call this part alpha x. And then this is d alpha dx over here. So you can see, when will this part be minimum? See the structure? This part will be minimum when x is equal to 0. Right? So if you put the, and what is x is equal to 0? X is equal to 0 means rho by rho C. That means rho is equal to 0. Where is rho equal to 0? Surface. There is no matter over here. Rho is equal to 0. So if I put x is equal to 0 over here in this expression, then you can check for yourself that this is the relation which we will get. M by r equal to 4 by 9. Interestingly, this is a very important result which has got no classical analog. When I say no classical analog, I mean to say that we can solve the same model for the non-relativistic case, but you have checked for yourself that there we do not get any sort of such structure. What is the reason? The reason is this type of structure, and this is the entire manifestation of the relativistic physics over here. So this is a very important, this is due to relativistic structure itself. No classical analog, no non-relativistic analog. Right? So this is more or less. So how you can say, sir, this is just m by r. Now you do the same old assumption, constant density. Then from there you will get a maximum mass m. But this is more general form. m by r equal to 4 by 9. Okay. Now next we will try to get an idea of Schwarzschild radius. Let's see how we get that. Okay, so previously we used this relation, right? Now using this relation we obtain the maximum mass, right? Now this time to find an estimate of the Schwarzschild radius, what we are going to do, we are going to use a different relation. Remember this relation we derived previously, and how we obtained it? From integrating r equal to 0 to r equal to 1. By the way, you must remember what is total mass m equal to 4 by 3 pi capital R, which is the radius, cube into the density. Now this time to get an idea of the Schwarzschild radius, we are going to use this relation. So here you see this is the density. Let me put this expression for mass over here, and then you must try to understand what we are doing. Previously in the pressure relationship, okay, pressure relationship, we wanted to find the maximum mass. So we extracted m by r term equal to some form, and there maxima minima we did the stuff. Now this time we want to get an idea of Schwarzschild radius. Now what is Schwarzschild radius? Basically imaginary boundary of a black hole. We don't know what is happening inside the black hole. Maybe the black hole is a pulsating star of dark matter or something else. There is something going on, some sort of vibration, like nucleus structure, atomic nucleus, maybe rotation, maybe vibration. We don't know. Why we don't know? Because at the radius of this imaginary star, event horizon, all the information is frozen out. We don't know what is going on inside, right? So basically you can approach that imaginary radius using the concept that we approach that radius when the pressure, central pressure, becomes what? Infinite. Because black hole means the entire mass becomes, everything blows up, right? So what's the pressure? What's the density? Infinite. What's the pressure? Infinite. So this is what we are going to do mathematically. Remember, mathematics is just a tool. Before doing any mathematics, we must have some idea of what we want to do. Remember trigonometry, using a relation we can derive in various forms. Like a tree has got so many branches, using a trigonometric relation several times we can arrive at various branches, right? So this time what we are going to do, it is important, we want to find when PC becomes infinite. Okay, now let's see what are the ways of approaching. So this is the relation. From here, why I am choosing this form? Because previous expression P, it didn't have any PC, that was not useful, but this form has got PC. Now when we have got PC and this is got square, then something comes to mind, quadratic equation, right? So let's write down the quadratic equation over here. So this is this quadratic equation we are getting from here after putting the mass. Fine, good. And this is very straightforward answer. PC is equal to this thing. Now look into the structure of this. What is the structure looking like? This is some term, this is some term. Now you will think, okay, when does PC becomes infinite? This blows up, something like that. You can think of it. But even more interesting thing is happening inside over here. Look, this is plus minus something root. Okay, now this entire thing PC will make sense only when this term is positive. Isn't it so? So let's try to attack this problem from this point of view. So this is positive. So what is this beta? This is the structure of the beta. This must be positive. Now for something to become positive, there must be a limit where it becomes 0. It is much easier to find 0 than positive. So if I put beta equal to 0, then you will say, you check this for yourself, put this equal to 0, you will get this sort of relationship. 2n by r equal to 1. And what is this? What does this mean? R equal to twice m. And this is the Schwarzschild radius. Okay. So you see, using very simple arguments, instead of looking for PC when it becomes infinite, we are right now looking into when PC makes sense. When the structure inside the PC becomes positive, then PC will make sense. Okay. And using very simple mathematics, we have gotten near the Schwarzschild radius. So using a very simple solving the TOV equation with constant density, we have not only obtained the expression for pressure, we have obtained also the maximum mass by radius limit. It wasn't just m, it was also m by r, but r is related to constant density, so basically maximum mass you can say. And next we arrived at the concept of this Schwarzschild radius. So these are the two very important takeaways from today's class.
এটা মানে ক্রিটিক্যাল কেস বিটাটা গ্রেটার দ্যান 0 হয় তাহলে তো
Yes, beta must be greater than 0. You can check for yourself. But somewhere it has to start from 0, and it is much easier to calculate. That's why I did this. Okay. There is another approach. In the expression you remember this term. Now if we convert that term into a PC and then put the denominator equal to 0, that means PC becomes infinite. That way you can also approach something like this. Okay. There are so many approaches. One is making the denominator equal to 0, another is using the discriminator form. Okay, a very basic mathematics.